November 17th, 1946. Naval Proving Ground, Dahlgren, Virginia. The morning air hung cold over the Potomac River, carrying the metallic scent of gun oil and cordite residue from the previous day's tests. A 26-inch armor plate, weighing over 60 tons, stood vertical on the firing range at the main battery, its massive bulk dwarfing the men who had spent 3 days positioning it with hydraulic jacks and precision surveying equipment. Salvaged from the unfinished Japanese super battleship Shinano, sunk by American submarine Archerfish in November 1944 before the carrier conversion could be completed, this colossal slab of Vickers hardened steel represented the absolute pinnacle of Japanese naval armor technology. The plate had traveled halfway around the world to reach this remote testing facility on the Potomac River, 50 miles south of Washington. Navy cargo vessels had transported it from Japan to San Francisco, then rail cars had carried it across the continent to the Chesapeake, and finally river barges had brought it up the Potomac to Dahlgren. The logistics alone had consumed 6 months and cost more than $50,000. But the Bureau of Ordnance needed answers. American intelligence had spent the entire war trying to understand Japanese armor capabilities. Now, with actual Yamato-class armor available for testing, the Navy could finally measure Japanese metallurgical achievement against American standards. Behind the massive plate, engineers from the Bureau of Ordnance's Armor and Projectile Laboratory made final adjustments to their instrumentation. Dr. L. T. E. Thompson, the chief metallurgist who had developed the Navy's standard armor penetration formulas back in 1931, supervised the placement of velocity measurement rings on the 16-inch gun that would conduct the test. High-speed cameras, positioned at carefully calculated angles, would capture every millisecond of the impact. Strain gauges attached to the plate's rear surface would measure how stress waves propagated through the steel. This wasn't just a ballistic test. It was a comprehensive scientific investigation into how the world's thickest naval armor responded to the world's most powerful armor-piercing projectile. At precisely 0900 hours, the firing command echoed across the range. A 16-inch Mark 8 armor-piercing shell, weighing 2,700 pounds and carrying the kinetic energy of a locomotive traveling at highway speed, struck the plate at 2,190 feet per second. The impact was catastrophic and instantaneous. The shell punched completely through 21 inches of the plate, its hardened steel nose penetrating deep into the face-hardened layer before the massive plate fractured. The entire slab snapped in 2 pieces, breaking through the impact point between the side edge and upper end of the gun port hollow cut into the plate's surface. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. When the test conductors examined the results over the following 3 days, they discovered something profoundly troubling. The Japanese plate, despite metallurgical analysis revealing inferior quality steel riddled with lamination defects visible under microscopic examination, had performed better than predicted by standard penetration formulas. The shell barely made it through. The 26-inch thickness should have been more than adequate to stop a 16-inch projectile at that velocity, according to calculations based on American armor properties. But the Japanese armor, with its substandard steel quality, had forced the shell to expend nearly all its kinetic energy before achieving complete penetration. The test report, filed in December 1946, noted with clinical precision that the plate exhibited excessive brittleness internally, with too much upper bainite crystal structure caused by too slow cooling during heat treatment. This metallurgical flaw resulted from applying pre-World War I British Vickers KC-type armor hardening techniques to plates exceeding 17 inches thick, processes never intended for such massive sections. The Japanese had essentially scaled up 1910-era British technology without understanding the metallurgical limitations. The steel quality was poor by American standards. Yet somehow, this inferior armor had nearly stopped the shell. But the real shock came 6 months later, in May 1947, when Navy metallurgists tested a thinner experimental Japanese plate. just 7.21 inches thick, designated Naval Proving Ground Test Plate number 3133. This specimen had been manufactured using a radically different heat treatment process. Intelligence analysis suggested the Japanese had reverse-engineered it from German Krupp KC new type armor, probably using technical data traded between the Axis powers during 1943 and 1944, when Germany and Japan were still sharing military technology. The American test conductors loaded 335-pound 8-inch Mark 21 Mod 3 armor-piercing shells into the test gun. These projectiles represented the improved designs developed in the late 1930s, with hard armor-piercing caps specifically engineered to defeat face-hardened armor without shattering. The first shell struck the plate at the prescribed test velocity. The plate stopped it cold. The shell shattered against the face-hardened layer, fragmenting into pieces that fell behind the armor but never penetrated. The test conductors were puzzled. They loaded a Mark 21 Mod 5 shell, identical to the Mod 3, except for an even harder, super-hard armor-piercing cap, developed specifically to penetrate the toughest face-hardened armor without breaking. This cap represented the absolute cutting edge of American projectile technology. The Mod 5 shell struck the plate. Again, the armor held. The shell penetrated partially, but failed to achieve complete perforation. The super-hard cap that was supposed to allow the projectile to survive impact against any face-hardened armor couldn't overcome this 7-inch Japanese experimental plate. When the metallurgists calculated the Navy ballistic limit, the minimum velocity required for a shell to barely achieve complete penetration, they discovered something that contradicted everything the Bureau of Ordnance thought it understood about armor. This 7.21-inch Japanese experimental plate, despite being manufactured from steel with the same mediocre quality as other Japanese armor tested, was the best plate of its thickness range ever tested by the United States Navy. Not good, not competitive, the absolute best, superior to every American armor plate between 6 and 8 inches thick that had been tested over 3 decades of development. The test conductors wrote in their official report, filed on November 20th, 1947, with barely concealed frustration and professional bewilderment. Obviously, we do not understand what it takes to make a high-quality Class A plate, since plate NPG 3133 should not have been so good from everything we thought we knew about face-hardened armor. The Japanese plate had inferior steel quality. Microscopic examination revealed the same internal defects, the same poor tempering, the same metallurgical flaws that characterized all Japanese wartime armor production. Yet this plate, processed using what appeared to be German heat treatment techniques, outperformed superior American steel processed using American methods by a significant margin. The uncomfortable truth was beginning to crystallize in the minds of Bureau of Ordnance metallurgists. For over 20 years, since American battleship construction had resumed in the late 1930s after the naval treaty limitations expired, the United States Navy had been installing armor on its capital ships that was systematically inferior to British and German armor. The performance gap wasn't small or ambiguous. Testing revealed American Class A armor was approximately 20 to 25% less effective than comparable British or German face-hardened armor when defending against large-caliber projectiles. This meant that an Iowa-class battleship, protected by 12.1 inches of Class A armor on its main belt, had protection roughly equivalent to a British King George V-class battleship, carrying just 9 to 9.5 inches of comparable armor, 25%. That number represented approximately 3 inches of effective armor thickness on the Iowa-class belt, 3 inches that could have been allocated elsewhere in the design. 3 inches that represented thousands of tons of steel plate manufactured, transported, and installed to provide protection that properly designed armor could have achieved with less weight. The implications cascaded through every aspect of battleship design. The armor weight budget for an Iowa-class battleship consumed approximately 12,000 tons of the ship's 45,000-ton standard displacement. If that armor was 25% less effective than it should be, the Navy was essentially wasting 3,000 tons of displacement on armor that didn't provide its designed level of protection. The problem wasn't the steel itself. This fact made the revelation even more frustrating for American metallurgists who took professional pride in their work. American steel production represented the pinnacle of metallurgical science. Carnegie Steel, Bethlehem Steel, and Midvale Steel, the three major naval armor manufacturers, produced armor plate with chemical composition, alloy, content, and mechanical properties that met or exceeded every specification. The nickel content, typically 3.5 to 4%, provided toughness and ductility. The chromium content, approximately 2%, enhanced hardness and resistance to brittle fracture. Small additions of molybdenum, usually around 0.4%, improved high-temperature strength and resistance to temper embrittlement. The tensile strength of American armor steel exceeded 100,000 pounds per square inch in the soft back layer, providing the ductility necessary to absorb impact energy without fracturing. The hardness ranged from approximately 650 Brinell at the face surface to 280 Brinell at the back surface, creating the decremental hardness profile that face-hardened armor required. The manufacturing process, from the open hearth furnaces that melted the raw materials to the massive hydraulic presses that formed the plates into curved sections matching each ship's hull lines, represented the cutting edge of industrial capability. So if the steel was excellent, if the manufacturing process was sophisticated, if American metallurgical science was second to none, why was American armor inferior? The answer lay not in what was manufactured, but in how it was tested. And the testing problem began in 1916 at Midvale Steel Works in Nicetown, Philadelphia, with an armor-piercing projectile that was too good for its own purposes. Midvale Steel Works occupied a unique position in American industrial history. Founded in 1867 as the Saucona Iron Company in South Bethlehem, Pennsylvania, the company had been reorganized in 1870 as Midvale Steel Works by William Sellers, one of the most influential American engineers and businessmen of the 19th century. Sellers had forced out the original founder, whose approach to steelmaking as an art of secret recipes and mysterious techniques didn't serve him well when those recipes failed, and he couldn't analyze why. Sellers brought scientific methodology to Midvale, hiring chemists and metallurgists who understood that steelmaking wasn't black magic, but applied science that could be measured, analyzed, and optimized. By the 1870s, Midvale had established itself as a premium producer of specialty steels. While giants like Carnegie and Bethlehem measured success by annual tonnage produced, shipping millions of tons of rail steel and structural steel to feed America's industrial expansion, Midvale focused on quality and specialty applications. The company produced high-alloy steels for applications where ordinary steel would fail, heavy artillery that had to withstand repeated firing without bursting, steam turbine rotors that operated at high temperatures and pressures, armor plate that had to defeat armor-piercing projectiles, pressure vessels for chemical plants where catastrophic failure meant industrial disaster. In the 1880s, a young machinist named Frederick Winslow Taylor had joined Midvale as a lathe operator. Taylor rose through the ranks with remarkable speed, becoming gang boss, then foreman, then chief engineer of the works, all before age 30. During those years at Midvale, Taylor developed the core principles of scientific management, the systematic study of industrial processes that would revolutionize American manufacturing. Taylor's philosophy was simple but radical for its time. Every industrial process could be analyzed, measured, and optimized through careful observation and experimentation. There was one best way to perform any task, and that best way could be discovered through systematic study rather than relying on tradition or intuition. That culture of scientific methodology, of understanding precisely why materials behaved as they did, rather than simply accepting empirical results, permeated everything Midvale produced. When Midvale metallurgists developed armor-piercing projectiles for the United States Navy, they didn't simply copy existing designs. They studied the physics of armor penetration, the metallurgy of projectile steel, the mechanics of how projectiles deformed on impact. They asked why projectiles failed and designed solutions to prevent those failures. By 1911, Midvale had developed a revolutionary new type of armor-piercing shell, designated the 8-inch Mark 11 Mod 1. Previous armor-piercing projectiles suffered from a fatal weakness that limited their effectiveness against the newest face-hardened armor. When these early projectiles struck face-hardened armor at any significant obliquity, at any angle substantially different from perpendicular impact, they shattered. The outer layer of face-hardened armor, created through a complex process of cementation and decremental hardening, achieved surface hardness approaching 600 Brinell, harder than most tool steel. This extraordinarily hard face could fracture projectile steel on impact, particularly when the impact angle allowed the hard face to act like a wedge, splitting the projectile nose. If a shell struck at more than about 15 to 20 degrees from perpendicular, measured from the normal line to the armor surface, the hard face would shatter the projectile into fragments before penetration could occur. A shattered shell was a useless shell, scattered pieces that might damage the outer surface of the armor but would never reach the magazines, machinery, and crew spaces behind it. The armor had done its job. The ship was protected. The solution, developed by British and German manufacturers in the 1890s, was the armor-piercing cap. A soft alloy steel cap fitted over the projectile nose would deform on impact, cushioning the blow and preventing the projectile body from shattering against the hard face. The technique worked reasonably well, extending the maximum obliquity at which projectiles could survive impact from about 15 degrees to approximately 20 to 25 degrees. But beyond that angle, even capped shells broke apart. This limitation meant that armor struck at high obliquity, such as deck armor hit by plunging fire at long range, was essentially immune to penetration because projectiles couldn't survive the angled impact. In 1916, Midvale metallurgists achieved a genuine breakthrough in projectile design. Through painstaking experimentation with steel alloy composition and heat treatment processes, they created projectiles with extraordinary impact resistance. The new shells used a specific nickel-chromium-molybdenum alloy steel, heat-treated to achieve a precise balance between hardness and toughness. Too hard, and the projectile would be brittle, shattering on impact. Too soft, and the projectile would deform excessively, losing its shape and penetration capability. The Midvale metallurgists found the sweet spot, a heat treatment that produced steel hard enough to penetrate armor, but tough enough to resist shattering even under severe impact conditions. These shells, soon nicknamed Midvale Unbreakable by Navy ordnance officers who tested them, could strike face-hardened armor at obliquities up to 30 degrees without shattering. For 12-inch and larger caliber projectiles manufactured according to the 1916 specifications, this represented a quantum leap in armor penetration capability. Armor that had been immune to earlier projectiles because of high obliquity could now be penetrated. Deck armor, particularly vulnerable to plunging fire at long battle ranges, suddenly became penetrable by projectiles that could survive the steep impact angles. The new shells arrived at precisely the moment the United States Navy was planning the largest battleship construction program in American history. The Naval Act of 1916 authorized 10 battleships and 6 battlecruisers, massive capital ships, that would make the United States Navy equal to the British Royal Navy. The first 6 battleships, designated the South Dakota-class, would carry 12 16-inch guns in 4 triple turrets, armor up to 18 inches thick on turret faces, and displacement exceeding 43,000 tons. The 6 battlecruisers, designated the Lexington-class, would sacrifice some armor protection for speed exceeding 33 knots, creating the world's fastest capital ships. The Washington Naval Limitation Treaty, signed in February 1922 and ratified in August 1923, killed that entire program. The treaty limited battleship construction and mandated that the United States scrap the 6 South Dakota-class battleships, all in various stages of construction, and convert 2 of the 6 Lexington-class battlecruisers into aircraft carriers while scrapping the other 4. Billions of dollars in naval construction evaporated. The Navy's carefully developed plans for achieving parity with Britain disappeared. American battleship construction, which had been proceeding at unprecedented pace, stopped completely. But the Navy didn't cancel its testing program. The Bureau of Ordnance had accumulated enormous quantities of armor plate, manufactured speculatively by Carnegie, Bethlehem, and Midvale, in anticipation of battleship contracts that would never materialize. 16-inch and 18-inch guns, manufactured for ships that would never be completed, sat in Navy ordnance facilities, awaiting some useful purpose. And the Navy had the new Midvale unbreakable projectiles, ready for comprehensive testing against the best armor American manufacturers could produce. Between 1921 and 1923, the Bureau of Ordnance conducted the most extensive armor testing program in American naval history at the newly established Naval Proving Ground at Dahlgren, Virginia. Dahlgren had been commissioned in October 1918, replacing the inadequate facilities at Indian Head, Maryland, which couldn't accommodate the ranges required for testing 16-inch and larger naval guns. The new facility occupied 4,300 acres along the Potomac River in King George County, providing a 20-mile test range over water. Massive concrete firing batteries supported guns, weighing over 100 tons. Reinforced bunkers protected high-speed cameras and instrumentation. The facility represented the most sophisticated ballistic testing capability anywhere in the world. The test program systematically evaluated armor plates from all 3 major manufacturers using the new Midvale unbreakable projectiles. The results revealed dramatic differences in armor quality, differences that had been masked when testing earlier, weaker projectiles. Carnegie Krupp cemented armor, designated CKC, which closely followed German Krupp manufacturing processes licensed to Carnegie in the late 1890s, performed reasonably well. Testing showed CKC armor was slightly better than captured German Krupp KC armor plates when both were tested with the Midvale unbreakable shells. The CKC armor met Navy specifications and was accepted for use. Bethlehem non-cemented armor, designated BNC, performed poorly. The BNC armor used an experimental composition with high carbon content, high chromium, and low nickel, attempting to achieve face hardness without the expensive cementation process. The result was armor that was excessively brittle, barely meeting minimum acceptance standards. Under impact from Midvale unbreakable projectiles, BNC armor exhibited dangerous failure modes, including large-scale spalling, where fragments broke off the back surface, even when the projectile didn't achieve complete penetration. Bethlehem recognized the BNC design was inadequate and abandoned it shortly after these tests revealed its deficiencies. But Midvale non-cemented armor, designated MNC, produced results that shocked everyone involved in the testing program. The MNC plates completely shattered the Midvale unbreakable 12-inch projectiles, as though they had no armor-piercing caps whatsoever. These projectiles, specifically designed to resist shattering and proven unbreakable against conventional armor, disintegrated into fragments when they struck MNC plates. The armor wasn't just good, it was 30% more effective than CKC armor against 12-inch projectiles, equivalent to armor 30% thicker. A 10-inch MNC plate performed like a 13-inch CKC plate. Against 12-inch Midvale unbreakable projectiles, the MNC armor performed better than anything the Navy had ever tested. The secret lay in the face layer, the hardened outer portion that gives face-hardened armor its name. Conventional face-hardened armor, whether Krupp cemented or Carnegie Krupp cemented, used a face layer comprising approximately 33 to 35% of the plate's total thickness. The face was created through 2 processes: cementation, which increased carbon content at the surface through exposure to carbon-rich gases at high temperature, and decremental hardening, which created a gradual transition from the hard face to the soft back through careful control of quenching and tempering. The MNC armor used a radically different approach. Instead of cementation, Midvale used only decremental hardening, but with an immensely thick hardened layer, extending to approximately 80% of the distance from front surface to back surface. This super thick face, combined with what turned out to be a fortuitous optimization of the tempering temperature that Midvale had discovered almost accidentally through trial and error, created armor with unprecedented ability to shatter projectiles. The thick, hard face acted like a massive wedge, catching the projectile nose and applying enormous shear forces that exceeded the projectile steel's ability to resist. The projectile would begin to crack at the nose, and the crack would propagate rapidly through the projectile body, shattering it into fragments before penetration could occur. Even the Midvale unbreakable projectiles, with their carefully optimized alloy composition and heat treatment, couldn't withstand the forces generated by impact against this super-thick, hardened face. The Bureau of Ordnance was impressed enough to order additional MNC armor manufactured for one of the cancelled battleships, recognizing that this armor represented a potential revolution in naval defense. If American battleships could be protected by armor that shattered incoming shells, those ships would be nearly invulnerable to enemy fire. Then the Bureau tested the MNC plates against 14-inch and 16-inch Midvale unbreakable projectiles. The results were catastrophic and immediately obvious. The larger projectiles still shattered against the MNC armor, fragmenting on impact as the 12-inch shells had, but the armor's resistance collapsed. The super-thick, brittle face, instead of gradually absorbing impact energy as the tough back layer would, failed by shearing and breaking apart in large sections. When a 16-inch projectile struck an MNC plate, the face would crack extensively, and large pieces of the hardened layer would break away from the back layer. The shattered projectile fragments, following these broken armor pieces, would pass through the compromised plate. Against 16-inch projectiles, the MNC plates performed no better than obsolete Harvey nickel steel armor from the 1890s, armor that was considered inadequate even 25 years earlier. The problem was scaling, a phenomenon that armor designers had not fully understood. Armor that worked brilliantly against projectiles of one size could fail miserably against larger projectiles. The super-thick, brittle face that shattered 8-inch and 12-inch shells couldn't handle the dramatically greater kinetic energy of 16-inch projectiles. The face would crack, and the cracks would propagate through the brittle material faster than the back layer could absorb the impact energy. Large sections would spool off. The projectile fragments would penetrate through material that had lost its structural integrity. The Navy had discovered a fundamental principle of armor design. Optimization for one threat could create vulnerability to a different threat. The MNC armor was optimized to shatter projectiles, and it succeeded brilliantly at that task against smaller projectiles. But against larger projectiles, carrying far more kinetic energy, the very characteristics that made the armor effective at shattering shells, the thick, brittle face, became the mechanism of catastrophic failure. This lesson should have guided American armor development for the next 2 decades. The Navy should have recognized that armor must be designed to defeat projectiles across a range of sizes, not optimized to perform exceptionally well against one specific threat at the expense of vulnerability to others. The lesson should have been clear. Don't make armor too good at breaking projectiles, if that excellence comes at the cost of fundamental structural weakness. The lesson was learned. Then it was forgotten. Or rather, it was remembered in a form that led to exactly the wrong conclusion. Instead of concluding that armor shouldn't be optimized to break projectiles, the Bureau of Ordnance concluded that armor must break projectiles, but it must do so across all projectile sizes. If armor could be designed to shatter shells without suffering the catastrophic scaling failures that destroyed the MNC armor, that armor would be ideal. The goal became to create armor that would pass what the Navy considered the ultimate test. The armor must visibly damage the projectile while stopping it. In 1923, the Bureau of Ordnance revised Ordnance Specification 751, the formal document that defined acceptance criteria for Class A face-hardened armor. The specification established 3 ballistic criteria that armor plates had to meet to be considered acceptable for installation on naval vessels. These three criteria would shape American armor development for the next quarter century, and understanding them is essential to understanding why American armor became systematically inferior to foreign armor. Criterion 1 addressed complete penetration. No more than half of the projectile body could pass through the plate and become detached from the remainder. This was a minimal form of what the Navy called the Navy ballistic limit, ensuring that armor would at least fragment shells, even if it couldn't completely stop them intact. If a shell hit armor and more than half the projectile body passed through intact, the armor had failed Criterion 1 and would be rejected. Criterion 2 addressed plate damage. The plate must not suffer excessive structural damage from the impact. Cracks extending beyond specified distances, complete fracture of the plate, or large-scale spalling where fragments broke off the back surface, all constituted failure of Criterion 2. The armor had to maintain structural integrity while defeating the projectile. Criterion 3 was the critical one, the criterion that would eventually prove catastrophic. The armor must cause serious projectile nose damage. At minimum, 1/3 of the projectile nose must be destroyed through shattering, breakage, chewing, shearing, or wiping. This determination was somewhat subjective, but photographs of previous acceptable test results provided standards for comparison. If a projectile passed through armor without suffering visible nose damage, the armor failed Criterion 3 and would be rejected, even if Criteria 1 and 2 were satisfied. The logic behind Criterion 3 seemed sound. If armor could shatter incoming shells, those shells would detonate prematurely, exploding, outside the armored citadel, rather than deep inside where they could destroy magazines and machinery. A shell that penetrated armor intact could detonate exactly where it would cause maximum damage, the base-fused armor-piercing shell's primary design purpose. A shattered shell, its explosive filler scattered and its fuse mechanism destroyed, was a neutralized threat even if fragments penetrated the armor. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. But there was a hidden assumption embedded in this logic, an assumption so fundamental that nobody at the Bureau of Ordnance recognized it as an assumption rather than a fact. The assumption was that projectile quality would remain constant, that the mid-vale unbreakable shells of 1916 represented the ultimate achievable level of projectile design. If projectiles remained static while armor improved, optimizing armor to break projectiles made perfect sense. Better armor would shatter shells that earlier armor couldn't damage. Ships protected by improved armor would be safer because incoming shells would be destroyed before penetrating. The assumption was completely wrong. Projectiles didn't remain static. Between the early 1920s, when American battleship construction halted due to treaty limitations, and the late 1930s, when construction resumed with the North Carolina-class, American projectile designers made continuous incremental improvements. Each improvement was modest, but they accumulated. By the mid-1930s, United States Navy armor-piercing projectiles were significantly stronger, more resistant to impact damage than the mid-vale unbreakable shells of 1916. The projectile bodies were strengthened through improved heat treatment processes that better controlled the balance between hardness and toughness. The armor-piercing caps were redesigned, made harder and more resistant to deformation, allowing them to protect the projectile nose more effectively. The cap attachment methods were improved, preventing the cap from being knocked off prematurely during impact. The nose profile was optimized through extensive testing, finding shapes that balanced aerodynamic efficiency during flight with structural strength during armor penetration. By the mid-1930s, the new 14-inch Mark 16 and 16-inch Mark 8 projectiles could resist shattering at higher obliquities and against harder armor faces than earlier designs. These improved projectiles were, by definition, harder to break, and the Bureau of Ordnance Acceptance Testing Specification responded by requiring armor to break these harder-to-break projectiles. If projectiles became harder to break, the logic went, then armor must become better at breaking them. Criterion 3 of Ordnance Specification 751 required that armor cause serious projectile nose damage. If improved projectiles resisted nose damage better, then armor must be modified to ensure it still caused that damage. Between the early 1920s and the late 1930s, American armor manufacturers gradually increased the thickness and hardness of the face-hardened layer, chasing an ever-retreating target of projectile breaking capability. The face layer that had been 33 to 35% of plate thickness in World War I armor grew to approximately 45% by the mid-1930s. By World War II, American Class A armor featured face layers comprising approximately 55% of total plate thickness. The face hardness increased correspondingly. World War I armor with surface hardness around 550 to 600 Brinell gave way to World War II armor approaching 650 to 700 Brinell surface hardness, harder than most cutting tool steel. Thicker, harder faces meant more brittle faces. The metallurgical reality of face-hardened armor is that increased hardness comes at the cost of increased brittleness. Steel can be made harder through heat treatment that creates specific crystal structures, but those same structures make the steel less ductile, less able to deform without fracturing. The thick, hard face that American armor manufacturers created to satisfy Criterion 3 of the acceptance specification was inherently more prone to brittle fracture than the thinner, softer faces used in earlier armor or in contemporary British and German armor. American armor manufacturers were solving the wrong problem, and they were solving it so effectively that they created a new problem nobody recognized. They were optimizing armor to pass Criterion 3, cause serious projectile nose damage. They were making armor that would visibly damage test projectiles during acceptance trials, ensuring the armor would be accepted by Bureau of Ordnance and inspectors. What they were actually doing, though nobody fully understood it until after World War II, was making armor more likely to fail by exactly the mechanism that had destroyed the Midvale non-cemented armor back in 1921. The super-thick, super-hard face layer was brittle. When large-caliber shells struck this armor at high velocity, the face would indeed damage the projectile. The armor would pass Criterion 3. Bureau of Ordnance inspectors would examine the damaged projectile, compare it to photographs of previous acceptable results, and approve the armor for installation. But that thick, brittle face was more likely to fail by a mode called plugging, where a circular section of armor surrounding the impact point would shear out and be pushed through the plate ahead of the projectile. Even a badly damaged projectile, its nose deformed and its armor-piercing cap torn away, could follow, an armor plug through the plate. The projectile would penetrate in damaged condition, fragmenting as it passed through, but it would penetrate nonetheless. The armor had technically succeeded at Criterion 3, damaging the projectile. But it had failed at its fundamental purpose, stopping the projectile from reaching the ship's vitals. The British and Germans made fundamentally different choices in their armor development, and understanding these choices illuminates why American armor became inferior. British armor manufacturers, testing their armor with British projectiles during the 1920s and 30s, maintained thinner face layers. British armor from this period typically featured faces comprising approximately 35 to 40% of plate thickness, substantially thinner than contemporary American armor. Surface hardness remained in the range of 550 to 600 Brinell, hard enough to provide protection against armor-piercing projectiles, but not so hard that the face became excessively brittle. The British made this choice because their projectiles weren't as strong as American projectiles. British armor-piercing shells, while adequate for their intended purpose, were more prone to shattering on impact than American Midvale unbreakable designs and their descendants. British armor didn't need to be as aggressive at breaking projectiles because the projectiles broke more easily. The thinner face provided adequate protection against British shells, while maintaining structural integrity against large-caliber impacts. German manufacturers followed similar philosophy, though their projectiles were stronger than British designs and comparable in some respects to American projectiles. German KC new type armor, developed during the late 1920s and early 1930s as an improvement over the original Krupp cemented armor, featured face thickness of approximately 40 to 45%. This was thicker than British armor, but substantially thinner than American World War II armor. Surface hardness was maintained around 570 to 620 Brinell, providing good projectile resistance without excessive brittleness. The thinner faces in British and German armor meant lower absolute hardness at the surface, but counterintuitively, this made the armor stronger in actual combat conditions. The face was less likely to fail by brittle fracture or plugging. When shells struck British or German armor, several things could happen, all of them preferable to what happened when shells struck American armor. The shell might shatter against the face, exactly as intended, or the shell might be stopped intact, its kinetic energy absorbed by the face and back layers working together. Or the shell might penetrate, but only after losing substantial velocity, ensuring that even if it got through, it would have minimal remaining energy to cause damage. Most importantly, British German armor was less likely to suffer catastrophic plugging failure where a circular section of armor sheared out. The thinner, less brittle face could absorb impact energy more gradually, allowing the tough back layer to provide support and prevent the face from fracturing catastrophically. American armor, with its super-thick brittle face, concentrated more stress in the hardened layer and provided less gradual transition to the tough back layer. Under impact from large-caliber projectiles, this concentration of stress in brittle material increased the probability of catastrophic failure. When post-war testing revealed that British and German armor was approximately 20 to 25% more effective than American armor against large-caliber projectiles at typical battle ranges, the Navy's metallurgists had to confront an uncomfortable reality. American armor was optimized to break American projectiles, the strongest armor-piercing projectiles in the world. But in actual combat, American ships wouldn't be shooting at themselves. They'd be engaging Japanese or potentially German ships, protected by Japanese or German armor, and firing Japanese or German projectiles that weren't as strong as American shells. American armor, designed and tested to break the world's most difficult-to-break projectiles, was overbuilt for the actual threat it faced in combat. The super-thick face that worked so hard to damage those nearly unbreakable American shells actually made the armor weaker against penetration by foreign projectiles that would shatter more easily anyway. The Japanese experimental plate tested in May 1947 proved this conclusively. Modest face thickness, optimized heat treatment according to German KC new type principles, mediocre steel quality with visible metallurgical defects, yet the armor outperformed thick-faced American armor manufactured from superior steel. The implications were staggering when Bureau of Ordnance analysts calculated the real-world impact. The Iowa-class battleships, commissioned between February 1943 and April 1944, carried approximately 12,000 tons of armor plate distributed throughout their structures. The main belt, 12.1 inches thick over the citadel protecting magazines and machinery, comprised roughly 4,500 tons. The turret faces, 17 inches of Class B armor backed by 2.5 inches of special treatment steel, added approximately 1,500 tons. The deck armor, comprising weather deck, main armored deck, and splinter deck, contributed another 2,000 tons. Barbettes, conning tower, and miscellaneous armor made up the remaining tonnage. Every ton of that armor, every inch of every plate, was manufactured to meet Ordnance Specification 751. Every plate was tested to ensure it would cause serious projectile nose damage. Every plate was optimized to break projectiles rather than simply stop them. And every plate was, as a result of that optimization, approximately 25% less effective than properly designed armor would have been. 25% of 12,000 tons is 3,000 tons. The Iowa-class was carrying 3,000 tons of armor that provided no additional protection compared to what properly designed armor 3,000 tons lighter would have provided. That 3,000 tons could have been allocated to additional fuel tankage, extending operational range from 15,000 nautical miles to potentially 20,000 nautical miles, or to additional anti-aircraft armament, the actual threat that would eventually make battleships obsolete, or to stronger torpedo defense systems, improving survivability against submarine attack, or simply 3,000 tons of weight savings that would have allowed faster speed, shallower draft, reduced construction cost, or greater ammunition stowage. The armor worked adequately in combat, which paradoxically masked the problem. No Iowa-class battleship ever suffered catastrophic armor failure from enemy fire during World War II. USS South Dakota, the name ship of the preceding battleship class using similar armor design philosophy, took hits from Japanese 14-inch shells at the Naval Battle of Guadalcanal in November 1942. Her belt armor rejected one 14-inch armor-piercing shell, deflecting it downward without penetration, despite the shell striking at relatively close range with high remaining velocity. The barbette of Turret 3 took a direct hit that caused damage, but didn't penetrate the 17.3-inch armored cylinder. South Dakota's armor performed adequately. The ship survived the engagement, was repaired, and returned to service. But the Japanese 14-inch shells that hit South Dakota were not mid-veil unbreakable shells. They were conventional Japanese projectiles, manufactured with Japanese steel and Japanese heat treatment, that were significantly more prone to shattering against face-hardened armor than American projectiles. British or German armor with thinner faces and lower surface hardness would likely have stopped those same Japanese shells just as effectively, probably more effectively, while weighing less and allowing that weight to be used more productively elsewhere. When USS Wisconsin was struck by friendly fire from USS Jarrett during the Persian Gulf War in 1991, 20mm phalanx rounds bounced harmlessly off the battleship's belt armor. The armor worked perfectly, but 20mm projectiles couldn't have penetrated 12 inches of any armor-grade steel, regardless of manufacturing quality or heat treatment philosophy. The test was meaningless. Wisconsin's armor could have been 25% thinner and still provided complete protection against 20mm fire. The paradox of American armor development crystallizes into this. The United States Navy spent 25 years, from the early 1920s through the late 1940s, developing armor that was quantifiably, measurably, provably inferior to foreign armor. Not because American metallurgical science was inadequate, not because American manufacturing processes were primitive, not because American steel quality was poor. American armor was inferior because American projectiles were too good, and the testing methodology optimized armor to defeat projectiles that enemy navies didn't possess. The entire design philosophy was a solution to a problem that existed only in Bureau of Ordnance acceptance testing, not in actual naval combat. The thicker face, the harder surface, the obsessive focus on breaking projectiles rather than stopping them. All of it addressed a threat that would never materialize. No American battleship would ever come under fire from American armor-piercing projectiles fired from American guns. The armor was tested against the wrong standard, optimized for the wrong objective, and installed on ships where it provided 25% less protection than properly designed armor would have delivered. By the time the Navy fully understood the problem in the late 1940s, the issue had become moot. The battleship era was ending. The last American battleships, the Iowa-class, were being placed in reserve, mothballed against possible future need. No additional American battleships would ever be constructed. The Montana-class, authorized but never laid down, was formally cancelled. The massive investments in armor development, the sophisticated testing facilities at Dahlgren, the accumulated expertise of 3 generations of metallurgists and armor manufacturers, all of it was becoming obsolete. Naval warfare was entering the missile age, and no thickness of armor plate could stop a supersonic cruise missile with a 1,000-pound warhead. the United States Navy was shifting its construction priorities to aircraft carriers, whose protection came from aircraft that could intercept threats hundreds of miles away rather than from armor that could stop projectiles that had already hit. The lessons learned from decades of armor testing were being filed away in archives, historical curiosities that would interest future researchers but had no practical application to contemporary naval construction. The Bureau of Ordnance quietly revised Ordnance Specification 751 in 1949. The new revision significantly modified Criterion 3, reducing emphasis on projectile nose damage. Armor no longer had to visibly break projectiles to be considered acceptable. It merely had to stop them, by whatever mechanism proved effective. The face thickness recommendations were reduced, bringing American practice more in line with British and German approaches that had proven more effective. The surface hardness specifications were lowered from 650-700 Brinell to 570-600 Brinell, reducing brittleness while accepting that projectiles might penetrate in better condition than earlier testing would have permitted. None of these revisions affected ships already constructed. The Iowa-class, the South Dakota-class, the North Carolina-class, all carried armor manufactured to the old specifications. Their armor featured thick faces and high surface hardness designed to break projectiles they would never encounter. The next class of American battleships, the Montana-class, never progressed beyond preliminary design. The armor problem was solved precisely when armor became obsolete. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.